Oh. Yeah.
Photosynthesis. It actually came out. Couldn't find why this itself. So this is galantamine, which is its like naturally natural. It's still the same thing. They're still used for the same thing, galantamine. But for galantamine, you actually have like hey, find the full. Aldehyde station. Galantamine. Galantamine. That. This is like the full synthetic version of that. That's the natural. Could be one and the same. They both serve still the same Alzheimer's medication. They still both act the same way.
I thought when I look at your poster, this molecule is just rotated. In other words, this end is that end. So this molecule is just oriented differently. Right? Bonded to it, and alcohol. Right down.
Well, that's okay. Well, that's probably, I was looking at it, it's like galantamine. How to use that. Mutation was it? That was different. I looked at galantamine natural. The actual plant they get it from.
That I don't know.
I'm assuming
It's an H here.
yeah, they had an H here.
Might
It's
just
not an
be-
H there. I figured it was probably a typo.
Might just be a typo.
It made
What was
this
your
originally they took the isovanillin and brominated it, and then they kept it and made a second reactor. Synthesized that, and then they reacted them together. That's all.
made the first ring? It has the functional. That it made another ring. Bicyclic. Nation. Final ring. I'm on the WebEx. Forward me if you want to know. Don't know how it'll look. I do know that these lights are horrible. Reflection dots show way more on the recording than probably you see. The fluorescent lights bouncing off that board bother you in person? Oh no. I didn't think it would the first time I tried to do a WebEx recording. I don't know if it's the camera, the angle. really nothing I can do without user. At any rate, chapter 10 and 11 is alcohols. 10 is properties of alcohol and how you make them. Chapter 11 is the actions of alcohols, aka what you can make from them. And then that's what I'm going to get through today. And then on Wednesday, I'm going to get through the basics of amines, acids, amides, and maybe a review of amides and esters, specifically their hydrolysis, which sets you up for understanding the macromolecules. Since I'm recording, I'm going to forward, so this is more planned, actual. So, should be a review, but have we named alcohols? Definitely should be a review. If I say this is methanol, good with that. Then another name for that is just to say methyl alcohol. So you could call it methanol or methyl alcohol. Historically, it goes by the name wood alcohol because that's how it was originally obtained. If you distill wood without any oxygen, you'll get methanol. So that's called destructive distillation. That's just historically. So modern times lead to much more efficient ways to make it. You can make methanol modernly by using carbon monoxide and hydrogen. That's also called synthetic gas. It's a very cheap way to make methanol. So methanol is one of those alcohols which is a staple of our economy and society. What do we do with it? Solvents, other reactions, making other things, etc. Ethanol could also be called ethyl alcohol. That historically goes by the name of grain alcohol. So if you go back to our fermentation experiment, we use sugar, grapes, juice. Could we have used a grain and then taken the grain, which would contain carbohydrates, break them down into sugars, add the yeast, and then we could have made ethanol. And of course, to get pure ethanol, would we have to have distilled it? And just like methanol, industrially, can you make ethanol from ethene, which has a common name of ethylene? So are we familiar with that one? Figure how many carbons in that? And common name ethylene. And what reaction would you do to make it into ethanol? That classic hydration of an alkene. In hydration, what do you add to the two carbons? HNOH. And Markovnikov says what? So in ethylene, is one carbon richer than the other in hydrogens, or are they exactly the same? So can we make ethanol very cheaply from ethylene? Then similarly, can we make isopropanol or 2-propanol from propene by the same acid catalyzed reaction? So in the hydration of propene, now do we have Markovnikov's rules in play? And 2-propanol also goes by the name of rubbing alcohol. So they're all feedstocks to make other things like solvents, paint thinners, etc. Synthesis. Are they also good examples of alcohols which miscible with water? That means miscible dissolves in. So do your alcohols C1 through C3 all dissolve in water? They all do. When you get to C4, as the carbon chain gets longer, do they become less soluble? And if you get to C8, will they be, again, pretty low solubility? But is the OH group a polar group? Which would explain why your low molecular weight alcohols dissolve in water. Should be easy, but is this the same as that? That the same as that? This is the same as that. So if we now go to this one and we want to practice our naming, what would you name? Would you give it? Cyclohexanol. Have to say 1-cyclohexanol. Say cyclohexyl alcohol. Before we go to this one, would you call this an alcohol or a phenol? That's a phenol. An alcohol? No, but does the phenol have an OH group? Does it have some properties that are similar to alcohol? But again, the phenol functional group is when the OH is directly connected to the aromatic or benzene. So we're not going to name this an alcohol, but would we say it has a higher solubility in water than the corresponding non-OH group? So properties of alcohols is that the low molecular weight ones are all very soluble in water. This would not be tremendously soluble, would have a little bit of solubility. This would certainly be more soluble than cyclohexane, but far less soluble than the lower molecular weights. This is not an alcohol at all, it's a phenol. And then when you get to these, now you have to decide your functional group priorities. So in a hierarchy, would you say the all trumps the E? So that's sort of how you learn nomenclature is each time we introduce a new functional group, it's going to get a higher priority than anything we've studied in the past. So if I say, how should we number that cyclohexene ring? If the all trumps the ene, which carbon has to be number 1? this way or would you go that way? So you would go that way and then you would say cyclohex. And again, if it's a 1, do you have to put the 1-all or could you? Cyclohexene 2-all. Cyclohex 2-ene-all. Could also just say cyclohex 2-all. So when you do it like that, the 2 go with the ene or the all. The ene. So that's really the only new wrinkle in naming alcohols now is that the alcohol functional group is going to trump the ene functional group. So of course, if we put a methyl there, would you change the numbering or just add 5-methyl? 5-methyl. If we put a chloro there, 4-chloro. As a quick review, would you say these 4 are structural or stereoisomers? For the final. Structural isomers. Go with those 2 are what relative to each other? Structural or stereo? Stereo. But these 4 are what to each other? So are those your C4 alcohols, which there's 4 of them if we disregard stereoisomerization. And so if you wanted to name this with a common name, you would just name that whole group followed by the word alcohol. So the common name for this would be butanol or butyl alcohol. Disregarding the stereochemistry, what would you call that as a group? That carbon unit. Okay. It is a butyl group, but we can't just name it plain old butyl because this is butyl. That's sec-butyl. So if you wanted to commonly name that one, sec-butyl alcohol. If you wanted to systematically name that, what would you do? This is just butanol, and if you want 1-butanol or butane 1-ol, then what are we going to do with that one? Butane 2-ol or 2-butanol, 2 acceptable ways to name that. And the common name for this is again sec-butyl alcohol. So Again, is that just a review of the C4 isomerization stuff? Follow it right along then. What are you going to name that as a carbon unit? If this is butyl, this is set butyl, then that one is isobutyl. So if you want to name this commonly, would you say isobutyl alcohol? And again, to make sure we're commonly using the common name lingo, I put it in quotes like that. If we wanted to name this systematically, which carbon has to be number one? How many more can you get in a continuum? So that would become propan one all. And again, if it's a one, do you just leave the one out? You can put the one if you want. But if that's propanol, we haven't named that carbon. And is that carbon off number two? It's a one carbon unit. 2-methyl propanol or 2-methyl 1-propanol. And then lastly, how do we name that carbon unit as a group? Tert butyl alcohol. How would we name it systematically? I go 1, 2, 3. That again, propanol. But now can you leave off the 2? Now the alcohol group is off number 2 of your propane skeleton, so you have to say pro and 2-all, and then do you still have to name this single carbon unit as 2-methyl? So again, do we end up different names if they are different molecules? And then lastly, if we collect all those up, are they C4H9OH or are they C4H10O? Same thing. Which one better suits you? Because then do you see that we're trying to talk about alcohols, which all have an OH group? Another chance for review. So would we say your low molecular weight alcohols are common solvents? Would you say they are polar protic, polar aprotic, nonpolar, something else? Are polar, and they are protic, and so do they assist with ionization type reactions? Are alcohols also potential nucleophiles? They are, so they can be solvents, they can also be nucleophiles. Is the OH a good leaving group? OH is not a good leaving group, but we can tinker with it to make it a good leaving group. I'm going to leave those up there for a second. We'll talk about those. So what I want to make sure we've went over is naming alcohols and how do we make alcohol. So we're going to talk about 4 different ways to make alcohols. 2 of them are a review. Number 1, what's X? Any halogen. So if I say, let's try to make isopropanol from a halide, which halide would you pick? Pick isopropyl chloride or isopropyl bromide, because which of your halides are very useful for leaving groups? Those 2. And if you're trying to make this alcohol, what would you use to displace it in an SN2-like reaction? Could you use hydroxide? And we talk a lot about SN2 chemistry. And would that work very well? We get any E2? Could we get some E1? Could we get some SN1? Like, could we potentially get all 4 modes of reaction? That was so can't say it enough, but is SN2 the most synthetically useful mechanism? Could you also get away with using just plain old water as your nucleophile? And you would still get this alcohol. So if you wanted to avoid the E2 or E1, you could avoid using hydroxide and just use water. So if I say which of these alcohols would be the best at being able to be made from the corresponding halide by SN2. In other words, which of those is going to be the best if we want to do SN2 chemistry? Because this is a methyl, this would be, and this would be. So again, we're reviewing for the final exam. Which would be the best substrate for SN2 chemistry? Methyl. Which would work? All of those. Which would not? Because the tertiary is too hindered to be able to do SN2. But could it do SN1? But if you wanted to ask, which would you use to displace the chloride in an SN2 fashion? That's really either. Which one is your most potent nucleophile? OH, but which one's also a more potent base? So if you wanted to do SN2 as fast as possible, you would choose, but you might get some competing elimination. If you wanted to do SN2 most efficiently without competing elimination, then you could choose water as your nucleophile. So in that sense, do we see that could we make alcohols like that? But of course, did we already talk about industrially, are these made by a different way? So that's a review of halides doing SN2. What's next? An alkene doing what? That should be fresh on the brain because what did we just cover? So what are the three ways that we can hydrate an alkene? Acid catalyzed hydration, oxymercuration, demercuration, and hydroboration, oxidation. So the final exam says want to make that alcohol, and we want to make that alcohol, and that's what we have to start from. How would you do? This is the Markovnikov alcohol, so could you use acid and water? Could you also use oxymercuration in the first step, followed by demercuration in the second step? That's the Markovnikov alcohol, so fix your notes. So how would we make the anti-Markovnikov alcohol? Think the HC brown, and we have hydroboration followed by oxidation. So really, for these two methods of making alcohols, things we've already covered. Spend a lot of time on them. I want to get to the other two and spend some time on them. So aldehyde, ketone. Again, what's the difference? So we can also review for the final. The final says which of those is an aldehyde? Which is a ketone? Adding to that, these are classic reducing agents. Sodium borohydride is not as strong as a reducing agent as lithium aluminum hydride, but either one of them will quote unquote reduce an aldehyde or a ketone to the corresponding alcohol. So before we get to the nitty gritty, let's just say you see that or that. The name reaction is reduction. Sodium borohydride, lithium aluminum hydride are reducing agents. No matter which reducing agent you use, you're always going to work that up in water, usually with some acid. That's important because overall, all a reduction does is add H across the double bond. H's. So in quotes there, 2 H's. And if I say we're gonna add H's across the double bond, your question should be, which double bond? So are we gonna add H's across that double bond? No. If we were to have that, would we add H's across that double bond? Potentially with a different agent, but not with these two. So these two are not quite as potent as pure hydrogen in a catalyst. They're going to reduce the aldehyde and or the ketone functional group. So just bear that in mind, and then realize that it's this double bond that we're going to add H across. So if you want to just be able to write the overall product, do you leave the benzene ring alone? Do you leave the carbon skeleton alone? Do you draw one of the two double bonds back? Do you draw the O back? And then you ask yourself, what do I add to the C? There, and what do I add to the O? And life is easy, because what do you add to the C? H. What do you add to the O? H. So does it matter which one gets which? Does it matter that you have to draw the H in on one of the atoms? So which one must you draw the H in? On the O, draw that C's H in? No. So if we take this ketone and do a reduction, what's the product? An alcohol. So how to prepare. As you make an alcohol. So is it pretty straightforward to get the overall reaction when you're doing a reduction? So you just have to know that these are the agents which will cause reduction. So analogously to this, which we would say is benzaldehyde, are we going to add the carbon skeleton in the single bond CO for overall product? What are we going to add across the double bond? 2 H's. And so which one again has to be shown? That one. Technically, do you have to show this one anymore? No. So whether you reduce an aldehyde or a ketone, what's the product? An alcohol. Aldehydes are always going to give you primary alcohols. Ketones are always going to give you secondary alcohols. So although they're both alcohols, there is a difference between primary and secondary. So as we'll see next semester, we also do reductions of acids, esters, amides with one or more of these. So you should be aware of these two reagents, but this one is the stronger of the two. So it would do it faster, more efficiently, but it'll also reduce other groups coming up. So mechanistically, what you want to think of either of those reagents has to make it sensible in your mind is H minus. So if I say, let's do this generically, if R prime is carbon versus hydrogen. So you might see it done that way. Then are we talking about either a ketone or an aldehyde? And that functional group, we said that a lot. So the carbonyl group is polarized such that the carbon's electropositive compared to the oxygen. And so if you now add to that this thought, that lithium aluminum hydride or sodium borohydride is a source of hydride ion. And hydride is the name for hydrogen as a negative with a full free lone pair of electrons. So would you say hydride could act as a nucleophile or electrophile? Nucleophile. And if you look at the carbonyl group, which atom is most electrophilic? The carbon. And does the oxygen have the potential to accept an electron pair? So this is going to be nothing really new if you've been practicing mechanisms. How would you say this, whether it's a ketone or an aldehyde, be acted on by hydride? I would say the lone pair is going to attack the carbon. And when that happens, to avoid 5 bonds on that carbon, what do we do? Flip up that, and then so is that kind of a similar theme that we've already seen with nucleophile? So when you get that, that's called an alkoxide. If you want the full mechanism with lone pairs, of course, could you draw those 2 lone pairs on the O originally? So now how many lone pairs would this O have? 3. So what do you guess happens when that is shown water or acid? Or both? The O negative just simply picks up a proton. I ask you to do the mechanism. Would you bother to take the water, draw its structure, grab the H, make hydroxide? Or if you have both of those, would you just grab a proton? So overall, what does a reduction add to the C? Where did the H come from? These hydride reagents. So you'd also add H to the O. Where did the H on the O come from? The second step, which is your acid workup. Good with that? So that's our third way of making alcohol. And the fourth way we're going to describe is called the Grignard reaction. And we have to thank Victor Grignard for that. This is going to flip the script on what you're used to. which is why it's important to understand themes and not memorize. I'll just do this generically, and then at the same time, with a specific example, what Victor Grignard found out was that if you took a normal halide, and I'll do it completely drawn out for full understanding, would we say that this carbon halogen bond is polarized like that? With the carbon positive compared to the halogen. So what Victor Grignard found was that if you just took magnesium metal with the halide and the solvent is critical, you need ether or THF for this to work well, and it needs to be no water. You get an insertion reaction. So you could show Victor Grignard's reagent like that. The specific example would be that. And this specific structure, I'm not going to draw other than to say, think of it like that. So if I say methyl chloride and magnesium come to mind. Doing the Grignard, because what does the Grignard do? Uses magnesium. So is that something new to your arsenal? The revolutionary idea and why it was worthy of the Nobel Prize is because it opened up a whole new methodology of making carbon-carbon bonds and alcohol. And most importantly, mechanistically, the carbon of the halogen is electropositive. When you insert the magnesium, does the carbon flip the script and become negative? Or I make fatal error. Is it really a full negative charge, or could it be just a partial negative? But for purposes of using it synthetically and understanding it, it's fine if you think of it as a methyl anion. So by inserting the electropositive magnesium, a carbon which has a significant negative character. So would you say this carbon is electrophilic or nucleophilic? That's electrophilic. But when we make the Grignard reagent, is that same carbon now nucleophilic? Okay. Technically, could you show it like this? With neither thing really charged? Is that going to help you understand that this is a nucleophile? No. So if you see RMgCl, did you think R minus MgCl plus? Because that's going to help you with the next step. So let us say we've now made methyl magnesium chloride, and we would make it from methyl chloride plus magnesium with what salt? Ether. And for purposes of synthesis, could you just say this Grignard reagent is methyl with a negative? And most importantly, if you show methyl with a negative, where is the negative charge located? On the H's or on the C? So of these three, which is the best way to help you with what comes next? That. And if we change this methyl chloride to butyl chloride or benzyl chloride, would you do the same analogous reaction? So if I use butyl chloride, would this carbon become the negative? If I use benzyl chloride, would that carbon become the negative? So do we have lots of halides that we can make Grignard reagents from? All right, and what do we get if we reduce an aldehyde or ketone? An alcohol. The reason we study that right before the Grignard is because there's an analogy coming. What can you add Grignard reagents to? Aldehydes and ketones. So the analogy is going to be, you can think of a Grignard reagent exactly like a reduction, because we're going to treat the same aldehyde or ketone instead of with H minus. Now it's just going to be a carbon minus. So generically, is this an aldehyde or a ketone? It's either. What would make it an aldehyde? If R or R prime were an H. So this is synthetically, the methodology is very useful because there's lots of halides to choose from. And are there lots of aldehydes and ketones to choose from? Once you make your Grignard, if you react it with any aldehyde or ketone, we just use generics. How are you going to fish out what's going to happen? Where your themes become really important. So would you say, if I switch to a generic, alkyl halide, is this carbon electropositive? Because the chloride is electronegative. But when we convert it to a Grignard, now is the carbon electronegative because the magnesium chloride is positive. And if you want, can you put a free lone pair on the R group and make it not just partially negative, but a full-on -1? Whether it is or not, we can debate that at some other time. But this is going to be your most useful species when you see this. Because then clearly, is this R group nucleophilic? So if this R group represents that one and you see this on a question, you simply say, oh, that's my Grignard reagent. I'm going to pluck off the MgCl and make that carbon a negative and realize that's your nucleophile. And then what is this carbon situation? Electrophilic or nucleophilic? This carbon is, again, partial plus, partial minus, electrophilic. So this is nucleophilic. Once you have that theme, what do you guess is gonna happen? And when that happens, what do you guess has to happen with one of those two? And do we get this alkoxide intermediate? Now, how many carbon groups are on the original carbonyl carbon? 3. And then just like with the reductions, after we add our Grignard, do we work it up with water and acid? And what do you guess the O picks up in water or acid? So why does the Grignard reagent fall under preparation of alcohol? Because ultimately, do you make an alcohol? Of the 3 carbon groups, how many came from the aldehyde or ketone? And the 3rd carbon group comes from the Grignard, which ultimately came from an alkyl halide. So we'll do 3 specific examples to show how we get different things. But just to review, benzyl bromide and magnesium in ether. What are we going to generate? The Grignard. So would you write the Grignard formula? What's a good way to think about it? Good way to think about it is these electrons are now more centered on the MGBR or the carbon. On the carbon. So is the Grignard a carbanion-like thing? All right, so let's take benzyl magnesium bromide, which we can think of like that, and react it with formaldehyde. And then we'll react it with acetaldehyde, and then we'll react it with acetone. So would the Grignard react with all 3 of those? The other way you can do it is just think about this group as being the carbon group that you'll add. So the key is I'm going to connect this carbon to that carbon. If I do that, this carbon to that carbon, anything happening to those 2 H's? Nope. Does something happen to this CO double bond? Because we've added to it. Does it become the O minus? And then in the second step, when we add water and a proton, what happens? H gets popped on the O. Gonna run out of board space. So I'm just going to put OH like that. So what you'll see is step 1, Grignard adds to aldehyde, and then step 2, worked up with water and acid. So in the end, is this sort of the segmented portion of the new molecule. And where did this group come from? The Grignard. Where did this carbon come from? That aldehyde. And of course, what happened to the C double bond O? Went away because it's been added to. And what does the H get? What does the O get? H. And then lastly, this we're going to classify as a primary alcohol because I'm going to erase all of this so we have this board to work with. That'll be able to let us go through the mechanism. So we're going to take the same Grignard with this aldehyde. So if I have benzyl magnesium bromide and this aldehyde, mechanistically, what are you going to do? I myself like to say, I know this is a Grignard, so I know this thing is really a positive. I'm going to knock that whole NGBr off as a positive, and therefore these electrons are on the carbon. So I'm just going to treat benzyl magnesium bromide as that carbon. So are these electrons more on the C or more on the NGBr? More on the C. Is the C negative? Does the C have a lone pair of electrons? And is the C with the lone pair of electrons nucleophilic? Once you get that practiced in your head enough times, nucleophile, where is the most electrophilic site? That carbon. So who attacks who? Nucleophile always attacks electrophile. What allows that to happen? The fact that this CO double bond can flip up. That alkoxide, and would that new connection be made? So that's the intermediate alkoxide. And what happens when you show that acid and water? The O picks up an H, and where would we be? In relation to what type of alcohol versus what we made here. So now that carbon, which is the OH, the alcohol, is now a secondary carbon or secondary alcohol. So where did these two carbon groups come from? one from the Grignard, the other carbon group from the aldehyde, and this H also from the, so this is a specific example of the only aldehyde, which is going to give you what type of alcohol product? Primary. So why do we get primary using this one? Because both groups on the carbon are, so where did this group come from? The Grignard. So if we want to say, what are we going to get overall when we add that same benzyl Grignard to this? You just say, I'm going to get a benzyl. And am I going to make the new connection to the aldehyde, which now has a methyl group and an H? Then what happens to this CO double bond? It becomes OH, and then this is a secondary alcohol. And if we follow that, what are you going to get when you just change this aldehyde to this ketone? Or you're going to get the same type mechanism, but this H will now be a methyl, and this H will be a methyl. So will it still be a secondary? It will now be a tertiary. So if we just want to predict the overall outcome of Grignard on a ketone followed by acidic water workup, what do we know we're going to add to the carbon of the aldehyde or ketone? The carbon unit of the Grignard. So like anything in organic chemistry, it's figuring out what connects to what. That's the biggest hurdle. So is this the carbon of the Grignard, which is going to connect to that carbon of the ketone? And when you're making that connection, will the double bond still be here? So again, if I'm using benzyl as my Grignard, there's the benzyl portion. This carbon is right there. Will these two methyl groups do anything or they stay? And what happens to the C double bond O? Erase one of the bonds, connect the O to what to give you your final product? And is that then a tertiary alcohol? So the Grignard, to summarize that, why does it fall under a way to make alcohols? Because alcohols are always the product. But equally important, is it a way to add a carbon group to another carbon group? So it's sort of the first foray into how we make carbon to carbon connections. That's why you get a Nobel Prize if you figure out stuff like that. And the last packet I gave you for our third test, we didn't cover it on the third test, but there was a whole sheet of practice with the Grignard. So on Wednesday, we're going to cover reactions of alcohols, properties of means and assets. So, got questions?